So okay, I guess I start with some logistics. So I saw I kind of went through you guys like proposal. I think it's good enough. It's quite good. So you should just go ahead and go along those ways, and also yeah, and remember that like you're supposed to submit the final project like in I think it's like we said in 2 weeks or so. I guess where was that? December 13th. Yeah, and actually today is already the second last class. We won't have class on the last week, like December 11th. So this will be the second last class, and and also like for what you're going to submitting for the final project will be just a screencast like what I'm doing here. So describing like what you have done for your project, like.
Could you present how, because I forget how to screencast the code.
Oh yeah, okay, yeah. If you use Linux, I can give you the code like what I'm doing like for screencast, but I don't know like for the other, for example Windows. But I guess you can Google that. And
yeah, last time we'll send you.
Yes.
About how to do that in the Linux.
Yes, and also I guess the expectation is pretty kind of I guess I always have like similar expectation. Is like just submitting, you have 1/4 of all the grade, like it's like 10%, I guess it's like 25%, and then if like you have the quality of like a weekly kind of like presentation in the department, that will be like 50%. If like kind of like quality in like university level, college level, the kind of presentation will be like 75%. And if like quality of like a national or international conference will be like 100%. And in terms of quality, what I mean is like on average. It's not like you're going to get an award or something. It's like what you're presenting is likely meet the average of whatever events that I described above. And so okay, that's basically all the logistics I will talk about. And so back to the material, we were talking about product of like two Gaussian distribution, right? So I guess like this is the equation we have like eventually. That if we have let's see this here, so if we have like basically we are, this is like we have like two observations, y1 and y2, right? X is the mean, and then we have the covariance. It can be a different covariance, and we kind of estimate the mean, right? So it's like doing kind of this kind the likelihood like py1 y2 given x, and maybe I can add like some knowing like sigma 1 and sigma 2, and then like this I assume that is independent, conditionally independent. So I have like py1 given x plus multiplied by py1 given py2 given x. So therefore we will have a product like this, right? And we derived last time that the product will be something like the new expectation, or like the in terms of like the likelihood of x, you have a updated mean. It's like a weighted variance, weighted mean of y1 and y2. You can think of y1 and y2 two kind of predictions, right? So or like two observations, not prediction, two observations, and you weighted them by the precision matrix. So it's reasonable, and more precise you will have a higher weight there, and the covariance will become the inverse of the sum of the precision. So in the sense like the new precision will be just the sum of the precisions of two observations. And also like of course like this is a likelihood, it's not in general a distribution, so therefore like it is not normalized to 1. What I mean is like if you integrate this over x here, it doesn't necessarily equal to 1. So we, yeah.
That should be Markov chain. So this should be
Yeah,
Markov
that yes, there will be a Markov chain in here actually here.
here. So that is will become the condition. If not Markov chain, that cannot be like that.
Yes, here we essentially assume there's a Markov chain here. Or like you equivalently is y1 y1 y2 are conditionally independent given x. So, but as I mentioned, just came back to this equation here, the normalization factor again is pretty lateral. Right? It will be basically just what should I say? It will be higher if like the observations are match better. So if you see like the y1 and y2 are more like differ more, then this weight will become smaller.
Smaller?
Yeah. I mean y1 and y2 is like farther apart, then like this will be smaller, right?
Why?
Oh, because okay, this is what this is a PDF of assuming I have a mean of y2 and covariance of this sigma 1 plus sigma 2.
So what is the covariance? Covariance is sigma 1 plus sigma 2?
Yes, covariance is sigma 1 plus sigma 2.
And what is the means on that?
Mean is y2. You can think of like, I mean like this can swap, right? Because you can think of like y1 is mean. You just have two values here. Like you can take either of them as the mean. It doesn't matter, right? So essentially, this just measure the difference between a y1 and y2. It's like a kernel, Gaussian kernel, essentially. Right? If,
so how you to interpret that? So if when the y1 is specifically bigger than, so previously you want to say what?
If y1 and y2 are farther apart, then this value will be smaller. So you think of like these are two observations, right? So if y1 and y2 matches, are closer to each other, so then the observations, like you make two observations, they match with one another, right? So then like you expect that like your prediction, your final prediction, will be more reliable. Yeah. So this weight here can be considered as like how reliable, like given these two observations here. And you can cascade more. You can not just y1, y2, you can y1, y2, y3, and so on. Like if you multiply further, then you have.
So
but yeah.
When that is close, so that is will be reliable. Will be good when y1 and y2 is close.
Yes.
So
then this will be high.
Will be high.
And then this will be kind of like okay, I guess as an exercise, I want to also show you like this is a product of like two Gaussian distribution, right? So we can use this to try to compute, let's say, the division of like two Gaussian distribution. Let's say I have like n I need to flip to that page here. Oh, where's that? Oh, okay, here. So let's say I have two PDF here. It's like oh, I guess I followed my notes here. Okay, okay, it's okay. Let me use y1 and y2 again, but I need to be careful because I'm using different notation in my slides here. So I can try to compute again the division of that using this equation. So basically it's like by inspection. Like I want to see like for example I start with
that is division.
Yes, that's division. So what I want is I want to have this multiplied by something equal to this way. So I want to have like y2 x2 sigma 2 multiplied by something. This is something. Then I want to get basically one of the term here is like x. Yeah, it's okay. Like y, I can write either on y1 x. Maybe it's better way x y1. Just follow here. X y1 and then with some covariance is equal to sigma 1.
Then x y1.
Yeah. So I want to multiply something. Kind of like using this equation here. I need to guess like, what is that something, such that like here the mean will become this guy. The mean this guy will end up become y1, and this covariance here will end up will become sigma 1. So basically, let's see, what should we guess?
So you do know that multiplication.
Yes, we're not following this equation here.
Yeah. So should be y1.
I
x1 x.
let's see. First of all, I want the covariance ended up with sigma 1, right? So I should have like some, I mean lambda 1 plus lambda 2 inverse ended up as sigma 1. Or like maybe it's easier to just use lambda. So I want to have the eventual lambda is actually equal to lambda 1. Let's see, what is that? So I want to
That's lambda 1. Lambda t maybe. Because that's 1 and 1. Should make a different.
oh yeah, that's I'm kind of confused. Yes, I'm sorry. This is a here is lambda 2. Okay, actually this part is easy, right? Lambda, this is a lambda unknown plus lambda 2 should be eventually we'll get lambda 1. Yeah, so it's obvious. So this one sigma, this sigma here should be just lambda, the lambda should be just lambda 1 minus lambda 2, right?
Yeah.
And sigma will be just inverse, so therefore should be just like that, right? So now then I should have, with this weighted sum, I have y2 weighted by lambda 2 plus this, I don't know, weighted by lambda 1 minus lambda 2
This for what?
for computing the mean here.
Oh, mean
Yeah. Yes. Wait, I need to be careful, like this is matrix. So my should be written this way. And y2 lambda 2 plus lambda 1 minus lambda 2, that is some unknown here, and this weighted, and I have the inverse of the final weight is, the sum weight is like just lambda 1, right? So it's a
Why should be like that? The equation. From where is it?
oh okay, it's from here, from there. From here,
Oh.
yeah,
Okay.
from this one here. So it's a the final mean, like after this multiplication, will be a weighted sum, right?
Oh yeah.
So
Okay.
so the weight here, like for this term, the weight is like lambda 2. The weight here is like lambda 1 plus lambda minus lambda 2. And this is some unknown, like mean, I don't know what is that. I have some unknown mean here. And then like of course like this weight has to be normalized by the sum of this position here is like just lambda 1 inverse. And so this together, oh, by the way, this is a variable. I just want to emphasize that this is a variable is equal to y1. So therefore, then I can just moving around, then I should have lambda 1 y1, where I multiply lambda on both sides, minus lambda 2 y2, when I move to the other side, multiplied by lambda 1 minus lambda 2 inverse, should be this unknown mean here.
From where that?
You mean here to here?
Yeah.
I just moved this multiply lambda 1 on both sides, right?
Oh yeah.
So I have this here. So then I move this term on from left hand side to right hand side. So I have minus lambda 2 y2.
Oh.
So then I take inverse of this one only, then have this.
Oh.
Yeah.
So that's all to get that's
To get this unknown here.
unknown there.
Yeah,
Oh,
this unknown mean here. So therefore that I now know that the unknown mean should be like lambda 1 minus lambda 2 inverse lambda 1 y1 plus lambda 2 y2. And then I also know this term here, this will be the this guy here, it will be Gaussian of y2 and lambda 1 minus lambda 2 inverse lambda 1 y1 minus lambda 2 y2, and the covariance here is a sigma 2 plus lambda 1 minus lambda 2 inverse.
That's a sigma unknown.
Sigma unknown is this guy, right? The sigma unknown, yeah.
So this one is come from this basically.
Yeah.
This one is come from there.
Yeah, this one is come from sigma
Sigma unknown.
this one multiplied by sigma this one plus sigma this one.
Oh yeah.
So therefore it's just this. Yeah.
Oh, okay. So you want to know that's
Yes, that have the equation, right? I already have that. They say now we have division now. So therefore this we have what? This divided by that. Or like the other way around. Let's see which one. Yeah, this is okay. Yeah, this divided by that is just equal to this divided by that, or something like that. Yeah. So, but you can see that like, I can use this multiplication equation also to compute the division. And now let's look at this division more carefully. Like after the division here, let me let me just give the final equation. So maybe I erase something, then I can just use this space here. So what I mean is finally we have this, right? So therefore this guy divide actually I use this divide by this.
So you want to derive the
Yeah. Well, we want to compute this division.
Oh.
Yeah.
Okay.
So so therefore we think of like what this one multiplied by what will get this one, right?
Yeah, that's right.
So then now this division therefore is just equal to I have what? This term over this term, so it's like Gaussian I have x as the variable, the mean is lambda 1 minus lambda 2 inverse lambda 1 y1 minus lambda 2 y2.
That's from where?
From here. I just copied this term here.
Okay.
Lambda 1 minus lambda 2.
But why that is x3?
Oh, this is x. This is not x here. Here I didn't write down the x here. I should have the x here.
So what is the?
This is just a semicolon.
Oh, that's
Yeah, it's like hard to write.
Okay.
Yeah, let me write a little bit better. So it's over.
Oh yeah, that's right.
Yeah, over this guy now. So it's a Gaussian y2 and lambda 1 minus lambda 2 inverse lambda 1 y1 minus lambda 2 y2 sigma 2 plus lambda 1 minus lambda 2 inverse. Okay, that we have the division equation. So something I want to kind of like point out here is if you look at this, like this is still a Gaussian, right? It still look like a Gaussian shape, right?
Yeah.
Yeah. Or I have some mean. Oh, sorry, mean is here.
Yeah.
I have some covariance here.
Covariance there.
but be very careful. Like it just look like a Gaussian, and sometimes it's Gaussian. But this does not necessarily. I mean, I write it in this way, but there's no promise that like lambda 1 minus lambda 2 has inverse. So it's kind of like I write it in a assuming that like this inverse actually exists. If it does not exist, then it will be just have lambda 1 minus lambda 2. We only have the definition for the precision matrix, but the inverse does not exist. But it doesn't matter, right? Because the Gaussian PDF, because remember what we have, the Gaussian PDF is essentially is like.
So if we don't have the variance, does it mean that it doesn't matter? Because we don't have inverse? It means that
Yeah.
have variance.
Yes, because in the Gaussian PDF function, we are kind of written this way, right? Something like x minus mu, this is upper transpose exponential, something like that, right?
Yes, that's right.
1/2. So this does not exist. It doesn't matter, right?
No.
All I also is that this sigma does not exist. It doesn't matter because here in the middle is really the precision matrix here.
So why it doesn't exist? It doesn't matter.
Yeah, I mean
If zero, it doesn't exist.
no,
It zero,
I mean this. Typically, people will write it this way, inverse.
Oh, yeah, that's
But
right.
this is in fact also like is equal to this, right?
Oh.
I mean, it's
Oh.
really
So the precision is 1.
the precision is here.
Is 1.
Precision is always exists. Precision always exists because like here it is saying the precision is lambda 1 minus lambda 2. This guy always exists.
Yeah.
But the covariance may not exist because the covariance is the inverse, right?
Yeah, inverse of precision.
And there's no. I mean, this expression is still okay. Like this expression is still will be defined,
Oh,
no matter what.
yeah.
But the covariance may not exist.
Might not.
Because
Might not exist. It means that 1.
no, may not exist meaning that like this is not invertible.
Oh, it's not invertible. Oh, okay.
Yeah.
Yeah. So cannot be inverted.
Yeah. Or even like I more not just it's not invertible, like the condition can be even looser, that like it may in that case like this covariance matrix still does not make sense because this may not may have, I mean maybe the inverse exists, even the inverse exists, but the covariance matrix is supposed to be positive definite, right? But this may not be. There's no promise that this has to be positive definite.
Yes, that's right.
Yeah,
The
because
vocab may not exist the inverse. Because that's impossible.
okay, actually, I should take it back. Like, of course, like without if the inverse does not exist, of course it does not exist. But even when the inverse exists, then still like this covariance matrix may not be a valid covariance matrix in the sense of a distribution, because a covariance matrix is supposed to be kind of non-negative, right?
No.
Yeah.
That's
So, but here, like the covariance matrix can be, I mean, in the sense that it has to be positive definite,
right.
but this covariance matrix can be like not positive definite. For example, like think of lambda 1, lambda 2 is just diagonal matrix.
Yeah.
So let's say I have lambda 1 is like 1, 1, 1,
Yeah.
1, and lambda 2 is like 2, 2, 2, 2, right?
Become negative then.
Then this is definitely negative, right? Minus 1, minus 1, minus 1. That would be it's a negative.
That is can be inverted actually. Negative can be inverted.
Yes, this one is okay. It can be inverted,
Yeah.
but
But the sigma is negative.
yeah, sigma is like
Become
negative. So what does sigma mean? Negative mean actually.
So there is no, the energy is negative.
that is pretty weird situation because it's negative. It means that like the your 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 variance in general, it does not exist. What does meaning it does not exist is like it can be like infinite. So therefore like you may end up that having a distribution is not exactly a distribution, but it can be something like this. So you have a mean maybe somewhere here, but then you just get like larger and larger, like
Yeah, that's right.
yes.
That's irrational.
So therefore like this thing, like be careful, this does not necessary to be a distribution. Like after this division here, it I mean this normalization factor can also like be
Non-distribution.
I mean yeah, this whole thing doesn't look like distribution because well I mean of course I always when we have this multiplication and division and so on, always like it's not like a distribution in the sense that it's normalized to 1, but at least like for the previous case when you have multiplication here, your it still looks like a distribution, just have a normalization factor here, but here like you will have in this case here, like in the previous case here, at least the covariance, variance and covariance will be positive definite, or like if you just think of the variance, at least like you will have variance is kind of defined, that the variance is going to be along any one dimension is going to be finite. But in this case you really can have like variance is infinite. Yeah, so
Covariance is infinite.
yes, variance is infinite.
So why variance is something like
in this case variance will be infinite, right, if you try to compute that, right, because if what's variance is like the deviation from the mean, right, deviation from the mean. So if you have any shape like this, right, if you go farther and farther away, the probability will get smaller and smaller.
Yes, that's right.
Yeah, from the mean. But for this guy here, you will just have like the
Bigger and bigger.
yeah, bigger and bigger, and if you try to compute the, of course you have this kind of normalize these things here, I suppose.
If we try to compute if it's something like that, the distribution bigger and bigger, if we try to compute the variance, this will be bigger and bigger.
The variance, if you basically, I guess your variance, think of like from here the variance is small, and then your variance is bigger, and then still bigger, and then like this and so on will become infinite, right, the variance.
Yeah.
So here is like basically this will have a situation like this. So your so-called distribution can go like shape like this. So
the it means that the probability will be bigger than 1?
yeah, that's exactly. I mean this one, this does not normalize to okay, because what we be careful, what we are computing here is not really a distribution. It's a product of like, or like product or division of two distribution. It doesn't necessary to end up into a distribution. Therefore, not just for the division here, it doesn't necessary to normalize to 1. Even this one, like, it doesn't necessary to normalize to 1. It's always not normalized to 1. You see, like this term in general, it's not equal to 0, right?
Yes, that's
Yeah.
right. For that case can be normalized to 1, but for division is sometimes not normalized to 1. It's not necessary.
This one, if you want to normalize, at least this term you maybe is you can divide that to normalize that.
Yeah. But for this case, it can be not distribution.
Yeah, for this case, it can have situation. It's not exactly like distribution. I'll just look at the shape there.
Yeah.
There's no way you can normalize that.
Because it will be bigger and bigger.
Yes.
Okay, I understand that. So the variance, yeah, that's really there is something. There's some situation will be like that.
Yeah, so therefore when you play with division, like just yeah.
So what after that? Already not there. So you want to cancel some component in here? No.
Actually, honestly, I don't know like when we are going to use a division. Like it yeah, it will happen. Like, but I didn't really play with that much. I assume that if you do a lot of
So
yeah.
for multiplication, if we know that the distribution that will become distribution, but for division, if we know that it will be not necessarily become distribution, something like that.
Yeah, actually, the shape will be very far from.
Yeah.
I mean, for multiplication, at least you will get something is like looks like a distribution. You will subtract to some normalization factor, but for division, it can be something, or like I should say, yeah, it doesn't look like a, yeah.
Because this component decide that. Because this component decide that.
Yes, this component will decide that. Yeah.
If negative will be.
Yes, if negative, then
will not become distribution.
Yes, if yeah.
That's right.
So okay, let me continue. Like what I'm going to. So I
This one also.
yes
Dr. Chen,
yes.
This one also become negative also. Yeah. Even plus with a sigma 2, but if it's negative, so this one also the variance will be negative for for the denomination.
Let's see. It's yeah, that's actually we can play a little bit on that. Let's see what happens. Let's see if I have let's look at 1D case. Let's see since we suddenly got interested on that. Let's copy it to a new page here. So let's see if I have a 1D case. Let me erase this change here. So for 1D case, let's say if I have like sigma 1 is equal sigma 1 square equal to 1, let's say sigma 2 square equal to 2, and then like let's say y1 let's just be simple. Y1 both y1 and y2 equal to 0 and see what happened. Okay. Then this term is 0, this term is 0, make it easy. Right? So I have I got x, and then the mean is just 0, and then the so-called variance, okay, the precision here, oh wait, I probably want to swap it. Let's see, lambda 1, lambda 2. maybe I put lambda 2 is equal to 0.5. Then position this one is equal 1 minus 2 inverse, or just the position is equal to 1 minus 2. Position is equal to minus 1.
Position is
Or actually the covariance, the variance also is equal to minus 1.
so we should find the covariance first.
Here I'm assuming 1D. So therefore, like as you see, sigma 1 is equal to sigma 1 square here. Just sigma 2 is sigma 2 square is equal to 0.5. Then lambda 1 is equal to 1 over lambda 1 is equal to 1, right? 1 over sigma 1 square. Lambda 2 is like 1 over 0.5, they're equal to 2.
Oh,
Yeah.
that's right.
So it's like 1 minus 2 is minus 1 here.
Okay.
Okay. I may take a win inverse, is still minus 1 here. Below is just is 0, 0, sum of sigma 1 and sigma 2, 0 is 1.5. It's some factor here, it doesn't matter. Wait.
Because that is
Wait,
zero
wait, wait.
because you say that y1 and y2 is 0. So this one, the mean is 0. And this one is...
Oh, I made a mistake here. It's not 1.5.
Fine.
Let's see. This is all 0, 0, 0. This is 0 here.
Yeah.
But sigma 1, sigma 2,
Sigma 2 is 0.5.
sigma 2 is a 0.5
Yeah,
plus this one is actually minus 1.
yeah, minus 1. That's right.
This one is actually minus 0.5 also. This is like 0, 0 minus 0.5.
Yeah, that's right.
This is kind of weird. But let's look at what this term is. 1/2. Let's see. What? 2 pi sigma square, right? Sigma square exponential.
Yeah.
0.
Yeah, a plus.
Oh, okay. Sigma square, right? 0 something sigma square. It doesn't matter. Like this. Anyway, it's 0.
That's become positive, because this is phi s, and phi s become negative, and negative become positive, so it will be exploded to the bigger. Yeah, something like that.
Yeah.
There is
Let me write the whole thing.
there is negative anymore in there.
Okay. So this is 0, right?
Yes.
And this is a there's a minus also. There's minus 0.5 here, minus 0.5. But it doesn't matter, like, this is 0 anyways, it's just exponential 0.
0 is 1.
It's just e. Yeah, this normalization factor is just equal to e over 2 pi sigma square. Yeah, agree with that?
If 0 is 1.
Yes, you're right, I'm sorry.
Yeah.
Yeah, my algebra is horrible. Yes, then it's 1, yeah?
Yeah.
Yeah, okay. The normalization factor down there is just 1. But let's look at upstairs. Up there. Up there is
If mean 0 also, that will be 1.
mean is not 0 here. Mean is x. Mean is 0, but this has an x, right? So the PDF is the PDF is 2 pi sigma square. Oh, actually, I have the sigma square. It's minus 0.5, but it doesn't matter, right? Here is
That's complex, because sigma square, square root sigma square.
yes, it's actually already pretty weird. You have something complex here,
Yeah. Something complex.
and then here is a exponential. Let's forget about the scaling factor for the moment. Hopefully, this will got cancelled actually.
Yeah, cancel from the below, because it's also complex.
Yeah.
Complex, cancel complex. Divide by complex is.
Let's say this is a x 1/2 x squared over sigma square is equal to minus 1. So it's like that.
Yeah, that's right.
So you will have a something like this.
Yeah, that's right.
Yeah.
That will be bigger and bigger.
Yeah.
It's mean that. Yeah. But why near x minus mu? Is is y mean x minus mu.
It's no. No. It's I just say why the general form is x minus mu. So it's here 0 minus 0.
Mm-hmm.
Yeah, it's just 0 minus 0. X is 0, mu is also 0.
So y in here is 0? Or because y is 0, yeah?
Yeah.
Y2 is 0.
Yeah, both y1 and y2 is 0.
Oh, yeah, that's right.
0.
Okay, so that's like so that's become not distribution, not 1.
Yeah, this is something like you get something totally weird. I just want to say. You can end up with something totally weird. But if with Porter, you always get something looks like a Gaussian thing, although it's subjected to some normalization factor there, but but division can be can have something very weird happen.
So but why in here should be lambda 1 minus lambda 2?
That's what we derived earlier, right?
Yeah, I mean
The precision is just the sum of the precision.
So that's yeah, derived earlier. So basically this is what you want to derive that. You want to divide this one and this one, but this one already has in.
No, here this equation we just copy from what we derived earlier, right? So we using the product equation. We show that if we have two Gaussian distribution divide like that, we will end up like this, right?
Yeah.
So this is what we showed like on the previous page there.
Oh, okay.
Yeah.
That's right. So this is the general equation. I mean that.
Yeah, this is a general equation. Like if you have like two x here, two likelihood function here in Gaussian distribution. If we want to divide them, we'll end up like this.
Oh.
Yeah.
Yeah, that's right.
So. Okay. What next? I want to give one motivation why we another motivation why we care about this product and division. So think of like, let's say if we have mixture of Gaussian.
Yeah, this is
Right.
this
Yeah.
is Gaussian. I did this.
So you did this.
Yeah, so many Gaussian mix.
So if you use so something like, for example, in 2D you can have like not just one mole here. In 2D maybe like you have one Gaussian here. This is the peak. Like for example, this is a peak here. This is going into me, like going out of the screen. So and maybe I draw this. How do we say that? Like leveling lines here. Like this maybe is like 0.5, and this is like 0.7. This is like 1, or like maybe 0.9, whatever. Then so this is like single Gaussian, right? This is a PDF, like in 2D, let's say, in 2 dimensions.
That is 2 dimensions.
Yeah, here I assume a 2 dimension. I just want to give a 2-dimensional example.
It means that multiplier also. Not
Yeah,
single.
yeah. This is like 2 variable, or like maybe like just do as 1D example. So I have this is a single Gaussian, right? So, but it may happen that like this, you have a distribution is like have multiple mode, right? It's like not just one peak, but you have multiple peak, right? So maybe a better description of a distribution maybe looks like that. But then in that case, you cannot use a single Gaussian to describe that. So you and if you use mixture of Gaussian, you can describe lots of distributions, right? Potentially, you can describe any distributions, right? Approximate any distribution. So
So it means that for this one is single distribution,
yeah.
and this one is mixture Gaussian distribution.
Yeah. For example, I can have here say 0.5 here. This is also 0.5 here, let's say, and this is a
Even in here
One
there is even
uh.
in here there is a 2 dimension. It's still single distribution.
yes. The single Gaussian here.
See, even there is 2 dimension, x and y.
Yeah, but this is only single Gaussian, right? So I can say a single Gaussian to describe that. But on the other hand, if I have another mode here, now we have a
Now
mixture of Gaussians, right?
Single Gaussian but multivariate.
Yes, yes, yes,
Single Gaussian but multivariate. If only like this. That's right?
yes.
Okay.
So for example, I look back to this 1D case here. So maybe I have this is just a one Gaussian. So it's just I have a PDF is a mean 0.5 and 1 variance, right? But this instead, what will be this? Maybe it's a x 0.5, also maybe 1. This is also like maybe this is 1.5, x 1.5, 1. But maybe like this is like have a higher contribution for this than this one. So the overall distribution can be like, let's say 0.33 of this plus 0.67 of this, let's say. Okay? This have a mixture of Gaussian. And you can have like even think of like continue our discussion like just previously. Maybe from our observations we derive not just one Gaussian. We have a somehow like our observation is not one point. Maybe like our observation is many points, and we group them together as one observations. And from that observation, we fit the model there, and then like we say that like from those observations like, we have a likelihood of what we describe observation 1 to be, this is like observation 1, to have a distribution like that. And then I have another set observation that we have like y to x here. Now, like what we have been doing like all the time, like if we want to take advantage both observations, we compute the likelihood. So assuming that like they are conditionally independent, those observations, so then it will become the product again, right? But now the product will be like product of mixture of Gaussians, right? For example, like I have one of the, from the first observation, I estimate the p to be this one. Maybe I have another observation, I estimate another p. Maybe this time it's like zero mean, maybe same variance, but this is like 0% pi, another variance, maybe 2, or maybe just same covariance, right? Like that.
So just multiply that both of
Yeah,
them.
then you need to multiply them, right?
And become previously study that we have
and we have the equations now, we know how to multiply them, right?
yeah.
And actually this multiply them, it will just say this, just try one term here, like 0.33, just basically this is 1/3, 1/4, like 1/12, right? It's 1/12 and x 0.5, 1 and x 0.1. Just consider this term, let's say. So this we have what? You end up nx. See if we remember that.
Yeah.
The mean will be the weighted sum of the mean. The weighted sum is easy because like the precision is the same in this case. So it's just 0.25, right?
Yeah, that's the mean.
Yeah, the mean. And then the precision will be like the sum of the precision. Here is also easy. So it's like just 2, so the variance is 1 over the precision. So it's like 1/2 here.
Yes.
And then like the normalization factor here is like difference between 0.5 and 0 is like 0.5. And let me just write it this way: 0.5, 0.5, 0, and sum of the variance basically 2. Yeah. So then, like, of course, you have this 12 here. So each term you can do like this. So you have 4 terms here. So of course, like, the problem is like that's a slight problem. So I probably won't go into this, but you need to group in groups if doing this kind of like mixture of Gaussian. If you have like lots of observations like this, you multiply them together. For example, you start with like all of them is like just mixture of two Gaussians. But if you have like kind of n observations there, then you will end up 2 to the n so many terms, right?
Oh yeah.
Yeah. So
And what is it? I mean, and then how many n in there?
so it's like y1, y2. If like let's say up to yn x.
So it means that if we have 1, 2, 3, 4. So
Yeah. When we multiply, there's 4 of them.
Yeah, 4 of them.
Yeah. If you multiply another one, you get 8 of them, and so on and so forth. Like you got lots of.
Yeah.
So then you need to group some of them and discard some of them and so on.
Yeah. That's right. I think there is no need 2 n, 2 power of n.
Mm-hmm.
No need 2 power of n, just n.
No, it's not 2 to the power of n. So for example, if I have 3 of them, let's say I have 3 of them.
Yeah.
So this multiplied this, I got 4 terms, right?
Mm-hmm.
Then I multiply by another 2,
Mm-hmm.
then I will get 8 terms, right?
Oh yeah.
So in general, it will be like 2 to the n if you have
2 n.
2 to the n observations. And if you have n observations, you have 2 of n terms here,
Okay.
Gaussian. But of course, as you go bigger and bigger, you just have to eliminate some of them. Maybe like some of these weights is small, then you can discard them. Better yet, you may, yeah, I don't want to go through that. Actually, the slides have some suggestion like how you may group some of the terms. For example, like you want to check like which one is more similar. So you want to group the similar one together, not just like group anyone. But because we only have 2 classes left, I don't want to get into this actually. And so since I'm talking about this mixture of Gaussian, I'm thinking that maybe we'll talk a little bit about EM. It's a
So what the purpose of this?
what?
What the purpose of these 2 Gaussian?
Oh, it's way to model like more arbitrary, more general distribution, because if you just have like use Gaussian alone, you can only model like a single mode distribution. You cannot model anything have multiple mode. Yeah.
To make a model.
Yeah, you want to have a
Precise.
Yeah, you want to able to model in lots of cases that it may happen that it's not just always okay. Your best estimate will be like this. Just think of some scenarios where you have like 2 possible scenarios that can end up very different prediction, right? For example, like if you're going to predict like how many people will be in the park like tomorrow, it will be very much depends on like whether tomorrow is going to rain or not. So assuming you don't know whether it's going to rain or not, then you probably have like 2 mode there, right? Yeah, you can have one mode is like okay, it's going to rain. It'll be like much fewer people. Like if it's not going to rain, it will be like much more, many more people.
And then should be together combined.
So therefore, like you will have in general, like if you only have like distribution like Gaussian, only a single peak, it's pretty limiting in terms of like its expressive power. Yeah.
Should be add with another peak.
Yes.
With this different condition, different situation. Okay, that's right.
Yes.
Or maybe in the electricity, something like we have 2 cable, and the cable has different noise source, and if we add to them.
Yes. If you don't know what's the noise source beforehand, of course, if you know it's going to rain exactly, then you become a single mode, right?
Yeah.
But if you don't know, then you just have to have like a. So it's like that. If you don't know what kind of noise exactly, then you will have like multiple mode there.
Yeah, and then also different mean of that.
Yes.
Because the first one is shift in here, and the second one in here, so different mean, and combined together will be create 2 model.
Yes.
Okay.
And so as I said, like So what comes next? Because we talk about what?
Expectation.
Yeah. I like to talk a little bit about expectation maximization, because we also already mentioned here, like maybe you have some observations, lots of observation. I'm trying to fit this using a Gaussian mixture of Gaussian models. Then the standard way to do it is using the expectation maximization. Let me go to another. Yeah, just prepared that like 2 hours ago. So hopefully, I talked about that like many years ago, but I didn't. Let's see. So basically, like for EM, you think of like you have create another page here. So the goal here is that you want to, again, essentially you want to fit a, so we say expectation. Honestly, I always don't remember where is the name actually coming from. So this is has been reinvented many times by many people, like from different disciplines. So or like EM. In the most general form is basically you're trying to have some here, like I just follow my notes here. So I will this time I will use X as observation here, observation, and theta is like some kind of like parameters that we want to fit these observations. So this is just trying to fit the maximum likelihood observation. So let's say maximum likelihood model. So I want to maximize, let's say, the theta such that it will fit this model best. So and I don't know why this again I have so many dots here.
You want to maximize the probability. So to find theta to maximize probability.
Yes, maximize. This is essentially the likelihood, like more precisely.
Likelihood, something like that.
Yeah, and you can see, like for example, for Gaussian, it's pretty simple. If I have a single Gaussian, I have say observation, I just compute the mean and the variance. That's it, right?
Yeah.
So that's pretty easy. But for mixture of Gaussian, it becomes not so obvious, right? For example, like if my variables here is basically like I want to fit this, like for example, I have many data points here.
For single Gaussian, the maximum actually at mean. That's right.
Yeah, that would be the mean and compute the variance, right? Single Gaussian would be very easy.
That's right.
But for example, if a data point like this, I want to fit the model, like with the observation like this, I want to fit this mean and variance here, covariance. Assuming 2D step will be mean and covariance here, then it won't be very good, right? Because you will pick the mean is in the middle here. It's definitely not a good mean here. So much better you want to have a mixture of Gaussian, right? Therefore,
Yeah.
and for mixture of Gaussian, again, like it won't be very obvious. So even though, like let's say I give a constraint here, saying that the mixture is mixture of 3 Gaussians, let's say. So let's say I want to fit into like this is weight 1, some Gaussian x, so theta 1, or maybe maybe I just use theta 1 to this mean the mu 1 and sigma 1, let's say, for
So no need to write a sigma 1 again. So this
no, I just group them like together here. I just use theta 1 here just for simplicity. Okay, and then like I want to fit into this, let's say.
There is 3.
Oh, sorry, it should be x. Yeah, 3 of them. Let's say just 3 of them. So then the question is, how do you fit them, right? So how do you fit them? Like just a guess. Like how should you do that?
Guess. Just find the mean on there.
Mean for which one?
Mean for all of them.
Mean for all of them, you will get something in the middle, eh?
Yeah, in the middle.
But here you have 3 means here, right, actually. Because you are kind of like a mixture. If you guess, let me just guess the good solution. Right? I guess good solution would be something like that. Right? Have like 3 clusters here, right? So I have should have a mean here, mean here, mean here, and have compute the covariance for each of these clusters here, right? But the question is like how do you proceed? Like how do you actually compute the and like how do you decide the
maximum?
The membership, like in the sense like for this data point here, you essentially consider this belong to this cluster, right? And this belongs to this cluster, right?
Using k-mean.
Yes, exactly. Actually, EM is a general case of k-mean.
Yeah.
So if you know k-means already, EM is actually if you use EM on a clustering problem, you will just get the soft k-mean algorithm. Yeah. So actually, it's like actually will if you try to derive EM, we will give you for this clustering problem using EM, you will go to soft k-mean.
So EM is soft k-mean.
Yeah, you shouldn't say. Actually, EM is more general than soft k-mean because soft k-mean is just for this clustering problem, right? Yeah. But EM is more generic. So, but if you apply EM on this problem, you ended up with the soft k-mean algorithm. So, but you know how to do soft k-mean, right? Do you remember? So, it's pretty simple, right? You first assume that okay, I assume some initial estimate of theta 1, theta 2, and theta 3. Right, so then like I start with anyway. This is maybe like maybe like I have some theta 1, theta 2, theta 3 there. Maybe a different color. Oh, I didn't change the color.
Go there.
Yeah, then based on that, like based on that initial estimate of thetas, you can design the membership of each of these data points here. Right? And if you use a hard k-mean, it would be like each data point can only belong to one of the cluster. But if you here like for soft k-mean, it will have a weighted sum. For example, like this point here, it can have a membership of this green cluster, but also have membership for this pink and also this what's this color? Cyan or what's the name of the color? Is light blue? I don't know what's the name of this color. I think it has a name here. Light blue. Okay. Yes. So and but of course like the weight for this green cluster will be larger, right? For this point here, maybe it's like 0.7 for this one, like 0.2 for this one, 0.1 for this one.
What point?
The membership.
Oh, the membership.
If for hard k-mean, I don't know whether you learn in the past you learn hard k-mean or soft k-mean. Hard k-mean will be like for each of this point here, it can only have one membership there. So one cluster. So I can this point definitely belong to this green cluster, and this point most likely belong to this green cluster also. And maybe this point is like in the borderline. It probably go to the green one, and this one go to the light blue one.
So it means that the member of this is integer. That's right.
Yeah, for the hard k-mean.
Hard k-mean is integer.
Yeah, I don't know whether it's called hard k-mean, but I know because it's soft or I don't know. Yeah. The other one is I don't know what it's like. But for the soft k-mean will be like you can have each point have a multiple membership of cluster. So you can have like this one, for example, in the middle, it may have like 0.5 for this green and 0.5 for this light blue, or maybe like 0.4 for this. Maybe have like 0.45 have a 0.1 for this pink even.
Yeah. So in between them,
Yes.
We cannot really hard to separate that.
Yeah, actually therefore like the soft K-mean have some advantage here. It's like for things in the middle, like it.
Yeah, something like diffusion.
Yes.
Okay.
And once you determine the membership, right? So more or less, then maybe these parts belong to the green, and this belong to the pink, right? This belong to the light blue, or maybe like this is actually too ideal. Like, well, I started there, I already got the correct clustering. It looks like. So if like my light blue is like not here, maybe maybe my light blue is.
Why the dot not in the center of that?
No, this is initialization. You don't know, right? You don't know at the beginning, right?
Yeah,
you just randomly fold the dot.
But after iteration, that will be inside, will be in the middle.
After you will get better.
Yeah,
so
will be in here. After all of done, will be in the center.
After many iterations, actually not just one, maybe several iterations. Let me get this one like maybe a more realistic like initial points here. Let's say I have like initially like have these 3 points here, 3 clusters. Then in this sense, I maybe I don't know, maybe this part will be the boundary for green and blue. Like this is like for green, like this is for light blue, and then like maybe I have like maybe this one have a border like this all are light blue and this is like the pink one. So then
why is the light blue?
Light blue is here. Let's say the light blue mean
in
here.
The middle.
Yeah, here. Let's say the initial mean is here.
Okay.
So then I compare this and this, then maybe okay, actually this is like not quite.
So we don't have any boundary on there. We should.
Maybe the boundary more like this. Maybe. Let me put the boundary like this. Let's say.
And there is no boundary in here. We should wipe all of this. So that is the.
No, because that's a mean way. So what I'm saying, like if you have determined the initial theta 1, theta 2, theta 3, then you determine the membership for each of these points here. So for example, for this guy here, for this point here, it looks like it's closest to this green dot here, right?
Yes.
Assuming we're using hard K-mean for the moment, it's easier. Then it would, then it will belong to this green cluster here. So this fall into the green cluster, and this fall into blue cluster and blue cluster and so on. Yeah.
Blue light.
Yeah. Ooh. Yeah.
Okay.
And similarly, like this belong to the pink cluster and this belong to the blue cluster.
Yes, that's right.
So, but then after you have this initial estimate, then you can update the mean and variance, right?
Yeah.
Like you say like this belong to the blue cluster, then you can from this points here you can compute the new mean and variance, right? So just based on these points here we can compute the mean, then the mean maybe will go to somewhere here, right? Maybe even closer to here maybe, right? So and then the new mean for the green dot maybe now will go to very much here, right?
Yeah, that's right.
And then the new mean for the pink.
This algorithm can find the global maxima then.
No. It will find okay. This will find the local maxima. That's no promise you can find the global actually.
Yeah, but if you calculate for all of them, so you can find the maximum of 3 of them group. 1 group, 2 group, 3 group, and we can find the maximum of them. Just compare in between 3. That's right. That is local maxima actually, but
it's local maxima. I don't know what. You basically it's an iteration algorithm.
Yeah.
Each time you iterate, right? So each time you try to re-estimate like for each of the data point, like which membership, like which cluster they belong to, and then like from their memberships we update the mean and the variance of the cluster,
Yeah.
each of the cluster as well.
Yeah.
Yeah.
And then after that we can find that three of them the global maximum. Yeah, local maximum actually.
Yeah, you will find the local maximum. Yeah, well, let's just go one more.
Yeah.
So after this, so we can we can update the membership. So I don't remember which points I have here, but anyway, so more or less like this way. So like the light blue is here, then maybe you will get the border is more like here now, move more like here,
Yeah.
and then like also for this guy here, oops, wow, there is many points here. Maybe the points over here, but then like this guy now have a pretty good boundary between the light blue and the red pink one now. Maybe more or less like this. Now this one more or less get the perfect cluster now. So next time you have the membership more or less correct, right? And then for this guy here,
still has some on there.
but then like you
more iteration.
you update the light blue one, it'll move more and more towards this side, right?
Yeah, that's right.
And then like next time this boundary will move towards here, and then the green dot also will move more towards here. Then eventually like you will get a pretty nice boundary, like maybe here, and then you kind of quite perfectly
in the middle.
Yeah.
So we can find middle of them, the center of them.
Yes, we will find the center. Yeah.
The K-mean.
Yeah, this is after you have the membership, you find the mean and variance update. That yeah.
So it means that in here K it means that clustering mean.
K is the number of cluster.
Number of cluster.
Yeah.
So how to find the mean of and variance is just measure the distance between this and to this and this to this.
Yeah, the variance will be like for each of the points you compute the difference from the current estimated mean from the data point, right? And then you compute the sum. Okay. I mean, compute the average square difference. Yeah. Then that would be the estimated variance, right? So that's it. Yeah, let's take a break. Maybe I will go a little bit more into the more general K-mean and not K-mean. No, I mean EM after the break.
So basically,